Okay, today I'm going to see if I can get through two lessons in one go, but we're going to first start off with Eulerian and Hamiltonian walks. Now, I've just got up in the top corner there. I always used to pronounce his name Euler, Leonhard Euler, but it's actually Leonhard Euler. So it's an Eulerian path, which I have a bit of trouble saying, so I'm going to struggle with that throughout this lesson. So an Eulerian path is also what we've so far called a traversable graph. So that's one where we can travel all the edges exactly once without taking our pen off the paper. Okay, so every traversable graph must contain an Eulerian path. So they use every edge of the graph exactly once. And they, for a path, so you can have Eulerian path that starts and ends at different vertices, or you can have an Eulerian circuit, and that starts and ends at the same vertex. So Euler produced some rules for this, and he found that to have an Eulerian path, your network graph has to have exactly two vertices of odd degree and no more. And you must, it also meant that you had to start at one of those with odd degree and finish at the other that has odd degree. Okay, so every other vertex in the whole graph has to be of even degree. And an Eulerian circuit only exists if all the vertices have even degree. So if there's even one odd vertex on a network, it can't possibly contain an Eulerian circuit. The reason why this came about is a problem called the seven bridges of Königsberg. Königsberg is a city in what was Prussia at the time. It's now a really weird part of Russia. Worth looking it up on Wikipedia. It's now called Kaliningrad, and it's a strange bit of Russia that's not actually connected to Russia anymore. But nonetheless, back in the 1700s, it was quite a pretty city. It's not quite as pretty these days, but it had these seven bridges. It had seven bridges going across the Pregel River, and there was a famous sort of problem of the day as to whether or not you could cross all of the bridges in Königsberg only once. But people found that if they wanted to cross all of the seven bridges, they tended to have to cover across one bridge more than once in order to cross every bridge at least once. So we can look at this by conducting a network diagram. And so what we can say is, let's call this up here vertex. I'll use a better color pen than that. Let's use that. Let's call that vertex A. We'll call this here vertex B. Call this bit of land vertex C, and this bit of land vertex D. So if we look at that, we've got our A, our B, our C, and our D. So there is two ways to get from A to B. So there's two nodes going from A to B. Okay. There's also two nodes going from C to B. I can get from A to D. I can also get from D to B. And I can get from C to D. Okay. Now, if we go around and count the degree of each of these, I've got a degree of 3 here. I've got a degree of 1, 2, 3 up here. Down at C, I've got a degree of 3. And here at B, I've got a degree of 1, 2, 3, 4, 5. So that one has a degree of 5. Now, as we learned before, the only way to create an Eulerian trail is if we have only two vertices of odd degree. So the answer to that is going to be no, because more than two vertices are of odd degree. So that means there can't possibly be an Eulerian trail. So we did this a while ago as well, but list two uppercase letters that are traversable and two that are not traversable. So for instance, a very easy example would be the letter C. If I think about C, I've really only got two vertices and one edge. Another example might be the letter D. So the letter D I can draw without taking my pen off the paper. However, I can't do the letter E. Because in order to draw the letter E, I'm going to have to take my pen off the paper. So traversable and not. And if you look at that, in the letter E, I've got one vertex with a degree of 1, I've got another vertex with a degree of 1, I've got a vertex with a degree of 3, and I've got another vertex with a degree of 1. So I've got far too many of odd degree. I've got to think of one more that's not traversable. Well, F will be another example for obvious reasons. Oh, and I've done that in a different color, but you can see that F isn't going to work either. I've got too many of odd degree. Okay, so as well as Eulerian paths, we have Hamiltonian paths and circuits. A Hamiltonian path is usually a little bit easier to find. That's just a path that joins every vertex exactly once, and it doesn't have to use every edge. Hamiltonian circuits can be a little bit harder to find, but they're not as hard as Eulerian ones, and that is a Hamiltonian path that can start and finish at the same vertex. There's no rule, unlike the rules for the Eulerian circuits, there's no rules for this, we've just got to check. So if we're thinking about whether or not they're traversable, we're thinking of using Euler here. So in order for it to be traversable, I need to be able to draw it. It needs to be either an Eulerian, a Euler path or a Euler circuit would make it traversable. In this case, every one of these vertexes has a degree of 2, so that is going to be traversable. So that's going to be that'll be fine. In this next graph, I've got a degree of 2, a degree of 2 at A and D, and at C and B, I've got a degree of 3. So I've got 2 of odd degree, exactly 2 of odd degree, and the rest are all even, so that will be traversable. In the third one, I've got every single vertex has a degree of 3. So that one's not going to be traversable because it's not going to create a Eulerian circuit or path. And then finally, in this last example, I've got, if I start at C and work my way around, that's 2 at C, 2 at A, 2 at B, 3 at D, 3 at E, and 2 at all the others. So I've got exactly 2 of odd degree. So that one will be traversable. But containing a Hamiltonian circuit, so a Hamiltonian circuit just needs to be able to go through every vertex exactly once, but for a Hamiltonian circuit, it's got to go through every vertex and return to the start, but it doesn't have to use every edge. So I can create a Hamiltonian circuit on this one. So it is that one does work. I'll give it a tick for Ham. For the next one, I can do this way. I don't have to use that middle edge for Hamilton. So yes, that one. Try. That one's going to be right. And this third one, which was not traversable, it is still there is still a Hamiltonian circuit. I can just go like that. I don't have to use all the edges for a Hamiltonian circuit, so that one will be correct. The last one, however, because I've got to come back to where I start, if I start here and go around, I can't get back to where I start. I hit a block there. I can't go on. So this is not Hamiltonian. Rightio, I've sort of paused and cut it in from where I was before, and I've jumped on to the next lesson, which is lesson 5. We'll do both lessons in the one video here. So lesson 5 is just more network problems. We're sort of building on what we did in the last lesson. It does include this new thing called the handshake theorem, which is that the sum of degrees is equal to twice the number of edges, which kind of makes sense because if you think of a very basic network just joining 2 vertices together, well, this vertex has a degree of 1, that vertex has a degree of 1 because there's one edge that joins the 2 of them. So I'm going to end up with 2 degrees giving me 1 edge. So it kind of makes some sense. But that's what the handshake theorem is, and that will come up maybe in some of those questions. This example that we're given here is we've got a principal of 5 different middle schools are meeting for the first time. Each principal must interview all the other 5 principals individually to learn about their programs, draw a network that represents all the meetings that will take place. So if I think about it, I've got 1, 2, 3, 4, 5 principals. Now, obviously, you don't have to meet with yourself, but Principal A is going to have to meet with every single other principal. Whoop. And then the next principal is going to have to meet with every single other one, but we've already drawn that line in. He doesn't have to meet up a second time with that person, but we do have to meet up with the rest. And the next principal, we've already drawn the line through to the first 2, so we've just got to draw the line to the other 2 principals, and then finally those 2 principals need to talk to each other. So just testing that handshake theorem, every one of those is going to have a degree of 4. So this has got a degree of 4, this has got a degree of 4, 1, 2, 3, 4, because they're all meeting 4 times. So the sum of the degrees is going to be, well, 4 times by 5 is going to be 20. So therefore, we should have 10 edges. Okay, and we can sort of test that out. Obviously, there's 1, 2, 3, 4, 5 around the outside like a pentagon. And then there's also 5 in the middle like a star. 1, 2, 3, 4, 5. So that works out. Okay, and then our final example for these 2 lessons is Mackenzie and her family are planning a trip to Fantasy Kingdom Amusement Park. They want to visit each area of the park and not have to pass through it again on their way to any other area. They want to do this using each of the 6 rides or walkways only once. So there's either rides or walkways that join the different zones. Mackenzie believes it's impossible, while her brother Nicholas believes that it is possible. Who is correct and why? Let's draw a network diagram and make some sense of that. So we've got the Blue Lagoon is one vertex. We've got Pirates Cove is another vertex. We've got Fantasyland is another vertex. And we've got Kitty City, and that's another vertex. And these are all joined. So Blue Lagoon and Kitty City are joined together. Pirates Cove and Blue Lagoon are joined together. Pirates Cove and Fantasyland are joined, and Kitty City and Fantasyland are joined together. And then as well as that, there's a join on each diagonal. The Sky Ride joining Blue Lagoon to Fantasyland, and the Sub Ride joining Pirates Cove to Kittyland. Now, if we go around and check the degree on each of these, this one has a degree of 3. This one, 1, 2, 3, has a degree of 3. This one has a degree of 3. And this one has a degree of 3. So what we know is that there's no Eulerian trail here, which means it's not going to be a traversable graph. So there is no possible way for Mackenzie's family to visit each of those 4 zones using each of those edges only once. So we would say something like, as the network is not traversable, Mackenzie is correct. I think I spelt Mackenzie a little bit different there. And what did she say? They will have to repeat a path. They will to see all zones. Okay. So have a go at the questions in there. Draw your network diagram up if it's asking for one, and make sure you follow the steps that are needed. And that's the end of that lesson.